Welcome to AI-based processing of financial documents. My name is Vahe, Martin, and Max. We are from SCDM. I couldn't schedule my sickness better, so my voice is a little bit shallow. I hope you understand me. If not, just raise your hand. I'll try to speak louder. Thank you very much for your interest. Can I just ask one question? By show of hand, can you show me who is from the financial industry here? OK, quite some people. Thank you. So SCDM is, in its widest sense, a data analytics company for financial institutions. We do a lot of things. We start with data management. We do IT systems, bespoke IT systems. We have products out there for investors in structured credit market, where we cooperate with Moody's Analytics now. And what we also do is process any kind of financial document. We need that for our internal processes, but we also do that as a service to banks and insurance companies. Today we want to talk a little bit how we do that, actually, because it's not a trivial task. But before we talk about AI and machine learning, the first question is obviously, what is actually the difference between AI, machine learning, and deep learning? So artificial intelligence is basically the idea of having a general-purpose intelligent machine. Okay? The easiest example is C-3PO from Star Wars, which is an AI-based machine. Okay? There are also other examples, like the Terminator. But that's the idea, is to have a machine that does actually everything, right? It's a general purpose. In the 80s, we started to realize that that goal might be too far reached, so we started to give special tasks to machines. The most famous one is obviously spam filtering. Everybody of you probably has one going for themselves. What it does, it's a very special purpose. It just filters out emails. It can only do that. It doesn't understand the context or anything. It just filters spam versus good emails. So it is a narrow artificial in practice. And then in 2010, basically, or starting 2010, the whole community went crazy, because as you can see, the concepts are actually very old. But everybody talks about AI starting 2010, and the reason is deep learning, because deep learning is a method of how to teach the machines, basically. And with this method, it opens tremendous areas where it can be used, one of which, for example, is the Tesla self-driving car. By the way, the problems that we might have, the ethical problems that we might have with general-purpose artificial intelligent machines still is there with a self-driving car. So there are, of course, a lot of philosophical issues around AI, which we are not going to dive into. What we are going to analyze is what is actually deep learning in detail, how is it possible, and what does it do for us. So deep learning, in essence, means two things. It means more data and more computing power. That's what is needed to create more hidden layers in a neural network. So the neural network mimics how our brain works, and the very first layers are 1 or 2 layers, and then the deeper we get, the more complex the task is, the more hidden layers we need. And the problem is, with normal CPUs, you're very fast at the limits of what a CPU can handle. And then with the invention of or the democratization even of GPUs, we can now use the GPUs, which are much faster than CPUs, to do calculation. And what we can also do nowadays is even distribute neural networks across a big computer network. But that's not everything. Plus deep learning, we have the democratization of AI, which is also very important. And Amazon is a very big leader in that, obviously. So what does democratization mean? It means that a small startup, like us, for example, we're a company of 200 people, we can actually fire up hundreds or even thousands of computers to do a simulation and then shut them down again without, being forced to buy 2,000 servers for a simulation, right? This democratization process is very important. There you have players like Amazon, but also Google, and a very new startup which just got, I think, just got purchased by Google is Kaggle, where you could actually build your models there and kernels and run them online, everything online. So the combination of deep learning and democratization of AI leads to this tremendous growth that we are seeing right now. So we are in the financial sector. What does it mean? The financial sector is, funnily, I think very, very funnily, not very digitalized. I say funnily because the only product that the financial sector actually has, or actually every product they have, is a digital product. Money is digital, everything else is also digital. But somehow, for some reason, this is from McKinsey, the processes within a bank or insurance company are not so digital. At the same time, and this is another problem, at the same time, changes within the financial industry come very, very slow. There are several reasons for that, regulation being one reason, and the entry barrier into the market is very difficult, so it gets seldomly disrupted. But the reason is not so important. What is important is that the business processes are more or less fixed, and they are not very digitalized. I'll give you an example. So one of our business lines is the valuation of structured credit portfolios. I don't know, for those who are not in a bank, structured credit is basically the collateralization of any kind of debt. Okay, it could be company debt, could be RMBS, so residential mortgages or any other kind of debt. Credit cards, student loans, you can collateralize them and then find investors for tranches. Basically what you do is you distribute the risk, which is horizontal to vertical to your investors. The market works like this, that you have like an asset manager who is purchasing these tranches, and for that is capturing everything in a digital system, right? And then out of that is a PDF report created, which I count as non-digital, that is sent over to a trustee who takes that report, all the trades that the asset manager has done, types them into their own system, so makes out of a non-digital product a digital product again, and then creates a trustee report, which is a report on all the investments that the asset manager has done. And that report is then made public to all the investors, the actual investors into the tranches. And what they are doing is they are taking that report, typing them into their own system to analyze it, and making a non-digital thing again digital. So it would be great if the asset manager had a shortcut to the investor and would just give him the data in a processable format. That hasn't happened since the surge of structured credit, and my bet is it will not happen the next couple of decades probably. So that's actually very frustrating if you think about it. So the goal is very simple, to have a machine that takes the PDF document, does all the work, extracts the data correctly, and gives you back the data in a processable format, right? That's the basic goal. In this diagram, you see here one brain, and I want to talk about what actually one brain in reality means. Because if you think about it, humans, we have one brain, but reality is we are not using the brain as one brain. We are using parts for special things, and that's very important. So, for example, to build a visual image of what we see, we use the visual cortex. But to understand what that actually means for us, we use the prefrontal cortex. So we use two different parts of the brain to read a PDF document that is printed out. And that's important to understand because that's the same way we are approaching AI in processing of financial documents. It means we have several parts that do several things. The first part is basically a section classification to understand what is this. You know, is this a table? Is this a chart? Is this text that I have to interpret? What is it? And then you have, if you visually interpret that, then you have to extract the data out of it, which is basically OCR, and OCR is also artificial intelligence. And after you have done that, you have a separate net that actually interprets that what you have extracted. So in this very simple case, it's not one AI, but actually 3 different modules that interact with each other to get to the final result. Our goal is to build the same democratization process that we have seen for, I can easy run AI models. There is Amazon recognition, I think it's called, or Google Vision API, where you can send over a picture and it interprets the picture and tells you back what's in the picture, right? And the same thing we want to build for financial documents. I want to send over a financial document, and it tells me, okay, this document is a financial report of IBM, and this is the data inside. Brings us also a little bit to the challenges. So I had to add this today, because I saw it yesterday. It was posted by Garry Kasparov, who is one of the actually the first chess player who had his alteration with AI, as he lost against IBM in chess, if you remember. And the funny thing is, so he's the world's best, or at that time was the world's best chess player, and he lost against a machine. And now 20 years are passed, and this is a very simple picture. And everybody can tell the difference between the Chihuahua dog and the blueberry muffin here, I'm sure. But if we ask Vision API or AWS recognition, they can actually not. They just see a dog all over. They don't see the blueberry muffin. So the simplest task, classification of things, is yet not really done, which brings us to the problem that we would like to take a table and understand where are the columns, where are the rows of this table, which is the first task, obviously. And even that is very difficult. The way it is done is basically convolutional networks, which are used for visual interpretation. And this is what we're building, and what Martin is going to talk about, how we are going to achieve that.
Yeah, thank you very much. I want to summarize shortly the theory we use for our applications. First of all, we have to start from a mathematical point of view. What is an image? An image is a 3-dimensional array with different integers as values, starting from 0, which a reference to black, moving to 255, which is a symbol for white. So from this point of view, we can represent each image as a vector, a mathematical object as a vector. And the first and most simple task we have to solve here is to find out when an image is similar. For that, we have introduced so-called distance measures. The mathematicians named it measure L1 or L2. The most simple one you find here, a simple calculation. We have 2 images represented as each image as a matrix. We are looking to the single values in this matrix. We are taking the difference in the absolute value, and the smaller the values of the matrix on the right-hand side are, as more close these images are in the neighborhood. So from that point of view, image classification, we can start with a very simple methodology. If images are very different, for example, an aeroplane, a car, or a deer, then it might be sufficient to work with so-called linear classification functions, as you can see here. You see here with different straight lines with different arrows. And if we are moving in the direction of the red arrow, the image moves more into the neighborhood of a car. And the probability that the image represents a car will become higher. But as soon we are talking about complicated things, like, for example, the classification of human faces, this linear methodology is not sufficient anymore. For example, looking to the face of a human, it's of course very individual. We have noses, we have eyes with different colors. And for this, we need non-linear methodologies. And for this, we can use so-called neural networks. Neural networks, they're working with bottom-up procedures because, for example, if we want to decide if on an image is a face, we can, for example, start with a simple task to find out if there is an eye on this image. So we are starting from the bottom. We are looking to simple characteristics faces typically have, like, for example, eyes. And later on, we come to a complex decision to which persons a specific picture belongs. All that is the methodology we're using are neural networks, and they are built up with different layers all different layers. They're representing a nonlinear classification function, and at the end, we are solving the task by assigning probabilities to results. Specific for the task, neural networks are used for many reasons. For example, mathematicians have used neural networks already 90 years for time series analysis. For the specific task of image recognition, we are using a specific version of neural networks, so-called convolutional neural networks. Because images, they have different invariance properties. I just started with the point, local features, for example, that a face has always two eyes. So starting with these invariance detecting eyes, is an invariance we can take into account in the learning of a neural network. Small translations, scaling, small rotations, or the situation that pixels in an image being close by have a higher correlation than other pixels with a bigger distance. So from that point of view, we are coming to a so-called convolutional neural network, where we have the workflow down here, and at the end with a task assigning to an image classification with different probabilities at the end. So what is the meaning of convolution? From a mathematical point of view, from a very general point of view, the difference of a convolutional neural network with an ordinary neural network is still that we, at least in one layer, we substitute matrix multiplication by the so-called convolutional operation. What we are doing here is we are running through the image like with a laser pointer, as you can see it here. We have a small matrix, which is a so-called kernel, and we have a large matrix, which represents the image. We are running with a small kernel around this image, and we are trying to find local characteristics. For example, that we find an eye or a nose and other things. Or we can identify, for example, edges. On the right-hand side, you see it. Finding edges, it's a very simple kernel with 3 dimensions, a very simple linear operation. Another point which is part of convolutional neural networks is taking nonlinearities into account. I show this with a very simple example. You see on the left-hand side image, we have black pixels, you have white pixels. Removing the black pixels and only end up with white pixels means we are removing all, if black pixels are labeled with negative values, we remove all negative values, which we can do with a very simple nonlinear function, which is the output is the maximum of 0 and the input. Of course, there are much more applications for that. Another very important point is so-called pooling of images. What we want to do, we want to make sure that if we change the input of a neural network, if we change the input a little bit, an image is a very complex thing with many data. We have perhaps millions of pixels. If we change the input only a little bit, we don't want to change the output a lot. And this is, for example, done by so-called pooling, which we can do with different operations, like building the maximum, taking the average, calculation of the sum. You'll find it here. You can also see we are making, with this pooling operation, from a matrix with 16 entries, we're making a smaller matrix with 4 entries only, which is also data reduction. So pooling helps us for many things, makes input representation smaller, makes the outcome more insensitive if we change the input a little bit. It reduces the number of parameters. It creates us to make the results more stable to small transformations, distortions, and other operations. And you can see it here. Here we have one picture where you can see it, how the pooling changed an input image if we apply, for example, maximum and the sum. Altogether, and we are solving here a relatively simple task, recognizing a car. Altogether, these characteristics of a convolutional neural network, this operation of convolution, looking for a local characteristic, looking for nonlinearities, doing that pooling, helps us finally to assign to different objects in an image the probability that these objects are in the image. This is a relatively simple task. Here we are talking about only the recognition of a car. My colleague Max will show you now, if we apply this to financial documents, the task is by far more complex and demanding.
Yeah, thank you, Martin, for the introduction. Now let me show you our concrete implementation of convolutional neural networks in the finance area. So as Vahe mentioned, we have reports. This is a RMBS report example, a structured credit product. And our clients demand us to extract specific data. In this, for example, a QZIP, what you see here in the green box. So these reports normally have between 40 to 400 or 500 pages, and the amount of extracted values vary between 100 to 400 values. And they are published normally once a month due to regularization. And whenever now you're your client, you come to us, you drag and drop your data into our S3 bucket. We are applying our machine learning model, and you get back the extracted results from us. We built our project on AWS. We're using 2 machines. The first one, the model factory for the training, and the production one I show you on the next slide. So whenever we now want to train a new model or retrain a model, we load our data into the EC2 machine, we run our algorithms, and then we evaluate our algorithm against to a model unknown test data set. If we are satisfied with the model's performance, we store this binary model into our model storage. If not, we have to go back, tweak our hyperparameters, check if the training data is correct, and retrain our model. So when we are in the production stage, we upload the models into our EC2 machine on a daily basis or update them. And whenever now we get a new report or clients drop a report in our bucket, this one is forwarded to our production machine, processed, the output stored in a JSON format, and again stored on S3. We were using TensorFlow as the machine learning library for our project for convolutional neural networks. And a lot of machine learning libraries are using computational graphs. Here's one example of one of our first algorithms we used for this project. Computational graphs, so like TensorFlow, the thing is you first, before running your code, you build the graph, and then what these deep learning libraries are doing, they can computationally optimize the calculations, so they're so-called lazy. And then when you start running, then your code, even then it starts with the calculations. So let us zoom in into the training module. So in these graphs, you can zoom in, out, check which modules are affected. And here you see when our first basic example we built on the Inception V1 model, which had very poor performance. Now we are using a more advanced one. And we had our own model built on it that's actually hidden in the 2 decoders, where the first decoder is the forward model and the decoder 1, the forward-backward model for the backpropagation of the training. We can process Excel files, PDFs, and images. So for the Excel case, we have written a Lambda function, abstracted the programmatic logic from the input data. So whenever we get a new report type, our financial analysts are able to set up a template, and we can very soon process this report. But most of our documents are PDF-based, as Vahe presented. So our first step is we convert the PDF to images. Then we run our first convolutional network to detect the values. This was like the green box you have seen. And then we run an OCR system on it to extract the values, which is our second convolutional network. Let me show you the process a bit in detail. So when we get the image inside, we run a pre-processing on these images. This means we scale them, we sharp edges to make them better for classifying. Then we run our convolutional network for the value detection, and our output are coordinates. You can see this in this example. This is a cropped image from the first slide I presented you. So in this task, we wanted to extract the QZIP. We put in the image, we run our CNN model, and we get coordinates out. And we can visualize the coordinates by drawing a box around it to also see for us if the algorithm works correctly. So the second step is then we want to extract the values that we just recognized in the red box. So we have the image again and the coordinates as an input. We again run a pre-processing on it. Then we have a word detection. This is a classical OCR module. Actually, we did the word detection in the step before with the CNN model, but here we do it on a statistical approach to cross-validate our results from the CNN. And then we start running our OCR model, which is another convolutional neural network. And the result is that when we apply this to the image and coordinates, we get our JSON file out of it. But we don't stop here. We provide more service to our clients. So when you have the processed report document, we match it to our database to see if we already have this report in our database. Because if we have it, we can build a time series out of it, and we can show our clients the performance of the report over time and already calculate them some statistics that are very useful for them. And another use case for us is we use these reports for our calculation of theoretical values for structured credit products. And these are OTC products, so they are not traded on the stock, as a stock. And you don't have a market value, so you need to derive a theoretical value for this. And this is where we use the data from. Yeah, and finally, our clients have access via an interface to our platform and can access their data.
So I guess we are run out of time. So we'll be around here somewhere there and maybe outside in the sun. So if you have questions later, or you can find us on, I don't know, Facebook, Twitter, LinkedIn, website. Feel free to ask us questions. Thank you very much.